Okay, we continue. It won't take long, but this is important for your analysis for beam. Yeah. Okay, so if you see a structure horizontal that's supported, and then there's an external force, so that is a beam. A beam is a structure that support loading. That is perpendicular to their axis. How you know their axis is you draw the central line along the body. Then you see the P is 90 degrees to the central line. All right. Okay, so that is called beam. Then beam as a start, we start with straight and constant cross section, but as you move on to more core subject, then the cross section will be different. Then you need to do section by section analysis. Okay, so our objective today is to change the one that you see in the previous chapter, distributed load plus the focus load, with the structure, with the support, right? You change it into free body diagram, then you calculate the reaction force and all this. Then it depends on the point that you slice, you'll get three forces: normal force, shear force, and moment. But in this case, normal force, we do not do analysis in the graphic form. So this section, we're going to convert the shear force and moment into diagram form, right? So later today, our focus to draw V versus X, means the X means from the reference point until the end of the structure, the X-axis, the length, and the Y-axis is actually the shear loading, the V that you analysis. Yeah. So you want to convert this diagram into this diagram, and also the moment diagram, M versus X. All right. Now normally, how we do it? How we do it? I'll do some introduction first. Okay, I'll draw something on the whiteboard. So usually when we analyze this kind of problems, we will draw the structure with all the forces. This is the so-called the static analysis. Means all the force and moment you do on that. After that, on your answer sheet, you use your ruler to guide, build some guidelines, right? And then if you see forces, also you make some dash line. Any forces focus load. Then you pick the space that you have there. One space is X, and the first graph is V versus X graph. The bottom one also copy M versus X. So it's always in this form. Then you don't need. Then you will see the relationship between the shear and the moment. Yeah. So this is the way behind the screen how you do analysis. Yeah. So I remove this one. I cannot. Okay, we continue. So the V versus X is called shear diagram. So in test or final exam, you'll see if the question about chapter 7, for sure you're asked to draw shear diagram and bending moment diagram. Okay, so the shape of that at the moment, you just have a look. I just have a look. Okay, a few characteristics to check your answer. If you have a point that is locked and there's a force pressing on it, usually you have a shear force in that location. You have a positive shear load in that position. Same with this one. Same with this one. It's only either positive or negative, depend on your analysis. And then the moment, okay, the moment you see as a like a slope of hill, right? It's a positive value, right? Now, how you know it's positive? You just imagine if you are this structure and you're pressing here, what will be the shape? The shape will be like smiling, right? It will be like a smiling shape. So if you have a smiling structure, your moment diagram usually will be positive. That is some general observation. And your diagram always return to zero. Mean it start from zero, then up, down, at the end it still return to zero. Means it will either go up or go negative. It will always start from zero, either positive, negative. Then at the last point of the structure, it always return to zero. Same with moment also. You always start from zero. I can either positive or negative value. At the end, it will return to zero. Yes. In this case. We will explain this one in next slides. So this slide will just give you some concept, what you expect to get if you ask to draw V versus X and M versus X diagram. A general concept first, then only how to do. Okay. Before I move on, just to recap, distributed load, when you see this one, always change to focus load. How to change? There's an appendix for that. Okay, so let's say we do this analysis, focus loss first. Focus load. If you see this diagram and we ask you to draw the shear moment diagram, support at A is a truss bearing. Truss bearing means something that can turn but cannot move. You can twist, you can turn it. Right? So turn means no moment there, but there is a force that allow it to move. Okay. Then is the ring. It's like a 3D printer motor that can move. Then C is mounted also. Okay. So you should able to convert this one in a normal force diagram. So you should able to find AY, AX, CY, CX. No moment because this is a bearing. Then you know there's no horizontal force. AX equals CX equals 0. Then you analyze this one, and you know that A and C split similarity. So you know 2, 2. So this one divide half. If not, then you can do all the force equals 0, all the moment equals 0 to find also. But common sense, you by looking at this, you know what is your AX and AY. Okay. Okay, first you draw free body diagram. You draw a structure, copy the shape, label point ABC, input the dimension, copy the focus load, or in this case is focus force. Okay, and we are using for positive force notation, which is go up positive, go right positive, anti-clockwise moment positive. That's why the green color arrow is pointing up. Okay, so this one is your homework lah. I assume you already know how to solve by using equilibrium equation. Again, when you write this one, it's always good habit to tell the examiner where is your reference point and what is the positive direction. Okay. All right. So you see this MO, it just means that on the structure, there's no moment. Okay. So this one, so here, X you don't have, right? You don't have X because on the free body diagram, there's no X. Huh? This one? Oh, this one. Yeah. A wrong notation. It should be negative. Negative. It should not equal to a moment. Moment at B. Moment at B. If you put moment at B, A will be turning this way. A is clockwise negative. CY is anti-clockwise, positive. So that's why minus AY plus CY. Because these equations are using moment equation. This equation, the second equation you see here is using force equation. So don't confuse between the two. Okay, so from here, you know AY equal to 2.5, which means you from here, you know. So from here, you know AY, okay, so this one minus CY is wrong. It should be positive. Right, should be positive. Wrong notation on my side. On my slide is wrong. Okay, but anyway, our focus is not on this one for today. Okay, so what is important is on the V and M. Okay, so V and M, we start to do analysis. You know your AY already, you know your CY. So you start from the left. Because your X0 here, maximum X is C, so you start from A, right? So you start from A and then you go to an X direction, X distance, we don't know, but you just define. So you draw a left-hand side corner, label A, and then give us a positive direction of your X, which is from this arrow, from this force AY, which is X to the right is positive, means your X will adjust from here to here. And then from the earlier section, that if the component is on the right, your shear force is go down and your moment is anti-clockwise. Here we do not put in the normal force because our intention is to draw the shear diagram and moment diagram. All right. Of course, if you still want to put in the normal force, also correct, but the information doesn't useful. Unless the question asks you to not this section, but earlier section asks you to do analysis on the internal forces. then you need to draw an N normal area here. You need to be sure when you need to put, when you don't need to put. That is important. So this is the first step when you want to draw the diagram. Want to draw the graph. So here is from your x will be from 0 to less than 2 meters. So means near to the focus load, very near to 5 kilonewton. This is do not have equal to, is near to 2. So catchy part is here. All right. So this one, just note that y arrow V go down and the blue arrow moment is going this way, because we're already using established sign convention, which is we use the positive sign convention. All right. Now from here, you can find your V, right? So you will get an equation. What is V, right? If you use the y equilibrium y equation, all the y equals 0. So you'll get one equation. Okay, so because we have forces and moments, so you use force and moment equation, equilibrium equation. So here Fy equals 0 and moment anti-clockwise is positive at A, because we start our x here from A and then continue until C point. Okay, we continue as you can see here. Okay, so from here, your V, you know, is if you do analysis, you know that your V is equal to this one. Yeah. Then your M, you have a linear equation here. MV, like how to find the M? If you put your finger here, your M is anti-clockwise. So M plus 2.5 kilonewton multiplied x equals 0. You arrive at M equal to 2.5x. Understand how to arrive this one? Who don't understand how you get this one? It's from this equation. Because we only want to see up to before the 5 kilonewton. We don't want to confuse ourselves with this force. We only up to very near to that force. Yes. Okay. So who don't understand? Who don't understand how to get this one? Anyone? If you don't understand, like, why suddenly I get M equal to 2.5x? Who don't understand? By using this equation, by using this one and this diagram, soft moment at this point equals 0. Or the moment at this point equals 0. So M, positive M plus negative 2.5x equals 0. Yeah. So those that don't understand, come and ask me later. So I assume all of you already know. So you have V and M. And you know that M is in the linear form. Y equal to mx plus C. C is 0. Okay. So again, recall back what I mentioned on the whiteboard just now. You copy your free body diagram. Then draw the dashed line. Your point A, point B, point C. Then start to draw the axis. Okay, if the question I set, there's a marks for all these hidden line and also the axis. You need to label V kilonewton because the forces you see in the question is 2 kilonewton. It's important to write the shear force plus the unit. And then this is your X. This is your X. So on the top is shear diagram, on the bottom is bending diagram. So you draw Y and X axis. So here is okay, here is M versus X. So your X is bracket meter, because you know that it's in meter unit in the question. So this is the general draft that you need to prepare before you go into the shape of the graph. As you can see, we already almost done already. The question almost done already. It's about 90% there already. Okay, first step, do the analysis, cut the thing to a certain x, do all the force equals 0, all the moment equals 0, you will get what is V. Why V only? Because we want to draw V versus X. V is Y direction, so only need to use all the force in Y equals 0. Don't need force equal X. Unless the question asks you, and the upper section will ask you to find internal forces. Right? So moment V, why we put a V? Because we want to eliminate all the unknown, many unknown here. So that's why I put in the location of V. Okay, so how to draw V equal to 2.5 kilonewton from X to 2? This is your Y, right? Y versus X. If your Y equal 2.5, how to draw? It's a straight line, right? So it's a straight line like this, huh? 2.5. Because this V tell you is a fixed value from X from 0 until 2 meter, near to 2 meter. So you draw a straight line from this equation. Y equal to 2.5 or V equal to 2.5 kilonewton. Draw until 2. And then highlight the area. Yeah. Then you move to the moment. Moment, you know that this is a linear graph. Y equal to mx plus c. You should able to draw y equal to mx plus c line. What is the value when x equal to? What's the value when x equal to? 5, right? 5, right? I'm 2.5 multiplied by 2. So here, when it reach 2, this value should be at 2. Sorry, 5. 2.5 multiplied by 2, you get 5 here. But this line is going up slope because positive m. Gradient. Y equal to mx plus c is a linear equation. Okay, so when x equal 2, m equal 5, you should able to know and then mark 5 in the moment diagram. Who don't understand up to this stage? How you get 2.5, how you get 5? Very straight, direct, huh? Okay, repeat the same for the another section. Repeat the same. Okay. So it's important you write the equation on the line in the moment diagram. Like in this case, m equal to 2.5x, this line. Okay. We have done for the first section. Now, now we do 2 until 4. We do 2 meter x, this x, x is between 2 meter until 4. Okay, so here is another section diagram that might confuse some of you. But again, you just shift your x to another side of the 2 meter. The structure is 4 meter, so you choose a section that far across the half of the section. Then you label x from A. Okay, you label x from A, and then this is 2. 2 is A to B, and then with the focus load of 5 kilonewton. So the distance of B to the cut section, it is you take x minus 2, right? This one. Okay, you ignore this one first. Okay. So yeah, Leslie question is why there's no equal sign here? Because we don't want to influence by the focus load, because 2 meter here got one focus load. We want to jump over. We don't want to confuse ourselves. We want to avoid the effect of focus load. Yeah. We just know or take note, or there is like a toe there. There's a toe there. We take note, but we want to see what happened after the 2 meter. Okay. So this section might be confusing for some of you because this method might be new to you. Right. So this one, label x until the distance that you slice. This distance must more than half. More than half or more than the focus load. Then this is 2. So the space here, you take x minus 2. Right, this space is x minus 2. And then the shear load and moment, you should able to understand already. Why we go down, moment anti-clockwise. Yeah. Yeah. So yeah. Okay, so ignore this 2m x and then less than 4. Ignore this one first. Yeah. Do the same. Equilibrium of force in y direction, equilibrium moment in v location. Still use back the same general equation. And always, if I set the question, this general equation got marks on it. I just writing this one, but you need to ask Dr. Nurul how he give you marks. How she give you marks. Okay, so still we want to find the equation that can help us to draw this section. So this, all the force equals 0, this one will help us to draw the V versus X diagram. All the moment in V equals 0 will help us to draw the moment diagram, bending moment diagram. Okay, so from here, from this free body diagram, all the force equals 0, you arrive at 2.5 kilonewton going up, 5 kilonewton go down negative, V go down negative, V equals 0. Here you will get one value of V. We use this one first. This one first. Ignore this one first. Ignore this one first. Okay. So your V is minus 2.5. Agree or not? Agree or not? Agree, Okay, go for V. V, M anti-clockwise positive. You stop at here, so you are seeing two moments. One is because of 5 kilonewton, which is anti-clockwise positive. One is A forces give you clockwise, which is negative. So M plus 5 kilonewton, which is here. How to get a moment is a distance that perpendicular to the point and the forces, which is this distance, right? So 5 kilonewton bracket x minus 2 minus A multiply x from the location of your V. So you have two equations here. Transfer these two information into the graph. Okay. How? Here, it's like y equal to minus 2.5. So here you are start from 2. So 2 minus 2.5 go to minus 2.5. Draw a line and then highlight with the pencil. Okay, remember to label minus 2.5. Okay. So when you draw V versus X and M versus X diagram, leave some space between the two because you don't know whether it's positive or negative. but you leave it some space for them. Huh? Okay, so this one you should be able to see. This is the y equal to ms plus c. The m is negative. C is positive 10. C is positive 10. So you substitute your x. So your x is 2, or you substitute your x is 4, you get 0, right? When x is 4, this is 10. 10 minus 10, 0. So you get the first point here. And if you really want to know what is your value when it's 2, is 5, right? So you substitute value x here. When x equal 2, your moment is 5. And because y equal to ms plus c, your m is negative, so it's going downhill. Then write the equation there. M equal to bracket 10 minus 2.5x. Then highlight the area between the x-axis and the line. The graph complete already. Any question? Any questions so far? No. Try to understand the strategy. The strategy of solving it. First, your free body diagram. Then find the reaction force first. Then slice it. Slice it from left hand side. Find a place before the focus load. Then do another set for after the focus load. Yeah. Okay. Now I add in some thicker, thick black line, just to show you what happens if you have a certain structure. Here is 5, right? How do you check your answer whether correct or not? You know that focus load is 5, right? If I go to section 2 meter, if I take 2.5 plus 2.5, I get 5. So when you have a 5 kilonewton, they always have a 5 kilonewton force on the shear diagram in total. This you need to check. Okay. Okay, we are focused, or we already done for the focus load. Of course, for static or dynamic, you will see distributed load. Okay, we almost done for the section already. I want you to observe what happens if you have a distributed load. You'll get a curve. Okay. The steps still same. The rest you later you can view my PowerPoint slides. The steps still same. Draw the free body diagram. Find the reaction force. Okay. Now, who don't understand why there is no AX? Yes. The AX equals 0 actually. Yeah. So from here, there's no pulling force and all this. Yeah. Right. Okay. In the diagram, why, my question is, why I need to split into 6 and 3? Why? Why? Those with diploma, why? Why? Yesterday we did discuss, right? On Monday we did discuss, right? Why triangular focus load? Where is the focus load? Here. 1/3 from the base. 1/3 over the base. Yeah. So that's why from the diagram, we always, first step, when you see distributed load, we convert distributed load into focus load. But still, we copy the shape of the distributed load. Just to remind that later when you draw graph, it is not triangular, it's not a sharp shape, but you will see a curve. Okay. Now this one, I just some notes lah. Those I think this one already covered in your previous chapter. Okay. So now how do you find distributed load if you are triangular? You use scale method, which is W that you know to the base of X will equal to the maximum weight, maximum load of 6, maximum distance of 9. This is a ratio equation. So you want to find what is the equation for W. So you take this triangular ratio, W will equal to 2 over 3x. In this setting, in this kind of setting, it not always this value, but we are using this triangular convert to find the W equation. Yeah, all right. So we can convert this triangular into this simplified triangular, which is x, and the W is 2 over 3x kilonewton per meter. Means we change 6 kilonewton meter into a general equation diagram. Why we need this one? Because we're going to draw V versus X and M over M versus X diagram. Okay. And then just to highlight the base, if you convert distributed load of triangular, the focus load will be quarter from the base, not quarter, 1 over 3 from the base. Okay. Yes. Huh? This one, when you learn about wing structure, then this one comes in. This one? This one is actually this line. 6 kilonewton per meter is the distributed weight of this triangular. Then we change it into a general one because this is 9 meter. What happens if you have a longer length? Then this doesn't apply anymore. 6 kilonewton per meter is at 9 meter. It's not here. Here is 0. There's some value here. It's not 6. This 6 kilonewton per meter is at 9 meter from this screw. We find the general equation for this triangular, which is 2 over 3x kilonewton per meter versus x. We want to make it in a bigger view. From the bird's eye view, what actually happened in these cases? This is a defined condition, but we want to change it into a general condition. Yes. Which one? Oh, this one? This one, Y27. It is when you transform this triangular 9 meter and 6 kilonewton per meter into a focus load. How you get 27 kilonewton? That one is, I think, in chapter 2 or chapter 3, when you study distributed load chapter. Basically, it's rectangular, divide half. Okay, if you take 6, multiply 9, 6 9 14, then divide half. Or area of the triangular. Yeah, right. So resultant force of the FR will be half x multiplied 2.3x. Mean this one, the resultant force of this one. This is a general equation for if you want to convert this distributed load into this black arrow. This FR is actually this black arrow. This one actually is black arrow. Is you are finding the area of this triangular. How to find area of triangular? Half base multiply height, right? Yeah, so this is just to convert everything you see into general form, general equation. Okay. Yeah, so this is important. Convert, if you see any time of distributed load, you need to convert the diagram into a diagram with X and the black arrow and the triangular. Okay. Okay, now you should be able to solve what is AY, BY. So this one, I leave it to you go home and solve it, right? You already expert already lah. This one solving equilibrium equation. Okay. What is important is to draw the V versus X, M versus M versus X. Again, we start from the left hand side. X to the right, and this X is we choose a distance that is more than the focus load location. Yeah. So this one we straight away direct pick a X that is more than the black arrow. Means this one more than the 27 kilonewton. And then the V go down, moment anticlockwise. We already explained why the black arrow is 1 over 3 x squared. We already explained why this dotted triangular is 2 over 3x kilonewton per meter. And from the previous equivalent equation, we found that your AY is 9 kilonewton. Correct lah, correct. Anticlockwise positive lah. Correct, correct. Okay. Go fight, go fight. Fight. Okay. Okay. So still the same strategy. We take our free body diagram and then draw the dotted line, prepare the axis V versus X, M versus X, put in the unit, and we start to draw. Because this is only have distributed load. So we only need to find two equations, one for V, one for M. So the V, we use all the force in Y equals 0. Okay, you find the first equation. By using this free body diagram, 9 kilonewton go up positive. 1 over 3x squared go down. So that's why there's a negative x squared. And then the V go down, negative V. Rearrange the equation, V put to the left, and the rest you move to the right. At the end, you arrive at 9 minus x squared divided by 3. This is a quadratic equation. Y equal to ax squared plus x plus a constant value. This value, what is your A? Your A is less than 1, which is negative. If your quadratic curve is negative A, it means you are having a set face. Right? Having a set face. So you should be able to see set face, set face in your V diagram here. Not smile face, because it's negative M or negative A value. Okay, then you do for the moment at V, M anticlockwise positive, and then this black arrow give you anticlockwise positive. 9 kilonewton give you negative value because it's clockwise. So you get M plus so and so equals 0. Yes. And in this case, we do not change the direction for my general hypothesis. In this case, negative means, yeah, arrow point down, but if I continue to use negative in my calculation, I still correct. Yeah. Okay, so the m will equal to bracket 9x minus x cubed divided by 9. X cubed is polynomial graph. Polynomial is like sinusoidal. Okay, so from the yellow color highlight, transfer into the graph. You should be able to do transfer into the graph. This is set phase. Start from 0 when x 0, your value is 9. When x 0, your value is 9 here. When the value is 9, it should be 0. It should be 0 also. But what is the middle point? You need to find. So you substitute, there's a value there. There's a value there which is 6 and 3 meter. You just substitute lah. Substitute. Okay. So there are two equations just now. All the force equal 0 in one direction. You get V equal to 9 minus x squared divided by 3. You can find the point where the shear loading is 0. Means your V0 solving solving quadratic equation. Your x will be 5.20 meter. Yeah, although this one is quadratic square, and you'll get square root, you'll get positive, negative value. We choose positive because your length is positive and not negative. Okay, so on the graph here, 5.2 will get 0. Yeah, your set phase will go through 0 here. Distance 5.2 meter. Okay, what is the value of V here? Is when your x 0, so this is 9 Newton, 9 kilonewton here. What is the value here? You substitute value. When your x is 9, you get a negative value there. Okay, it will be negative 18 if you substitute x equal to 9. Okay, do the same for m. Okay, when you have a distributed load, just need to take note. You need to do extra step, which is to find where is your zeros here. You need to find when what x is at what x v equals 0. Then copy that x to the m. X 2.5, substitute here. Your m is 31.2 positive value. So this polynomial graph, negative polynomial graph, is something like this. It's not a perfect circle, but it's shifted a bit to the right. And you label accordingly 3.2 and put in the equation. This might be challenging for those if you are weak in your mathematics. Might be challenging for those that you do not look, you never seen polynomial graph. Then it will be a bit difficult for you. Okay, so this is the answer expected for this one. Okay, so we are done for the moment diagram. So what I need to highlight here, you focus load. If you have focus load, you get a straight, sharp curve, sharp line. If you have a combination of, if you have a distributed load, then you have a curve. That one. Okay, so the rest, I go very fast just for info, right? You will see this kind in your senior years. Of course, in static, you will see also. Okay. But the method of analysis is the same like what you learned just now. Don't confuse yourself. The method still same. As you go deeper and deeper, especially go for structures, your lecturer like to look at delta x, mean very small distance, and then do elaboration on expansion of the equation. Okay, the rest I will skip, not skip lah, but go home and have a look at on the slides. Okay, notation of the way you cut. On the left always go up, on the right always go down, and then moment on the left will be clockwise, moment on the right will be anti-clockwise. Yeah. Okay, this one you go and okay. So this one is important, where you are given a distributed load and you need to calculate dV over dx equal to distributed load. Okay. Slope of the shear diagram will equal to distributed load intensity. Means from the graph, you can convert back to the real scenario. And differentiation, this one you see in the engineering maths later lah. Well, so just take note of these two, right? So differentiation will give you the W. Integration, you'll get back shear. Delta. And then this one is moment. If you differentiate moment, the slope from the moment diagram, you get shear. What does it mean? Just now we see two graphs, right? What does it mean? It means that application of what you solved just now. Just now you got two graphs, right? If the question asks you how many moments at this section, I do integration. If you do this one, you do this from here to here and here to here. Oh, give me 2 more minutes. 2 more minutes. Okay, what is important is this one. Okay, the rest you read. The rest you read. What is important is, okay, what I want you to see is this one. I assume you did understand what actually happening on the diagram. It's a combination of focus load and distributed load. So just observe the step. Actually, the first step is to solve like what you usually do. Solve for the resultant support. All right. And then draw the V versus M diagram. Draw the V versus M diagram. Okay. We already cover up to here. Okay. Observation here. If your V have a there is a correlation between the V and M. No, A is free N. Free N there, so there's nothing there. Only B. Let me flip if I miss out anything. Okay, have a look. These are all final exam standard lah. Have a look. Okay, all these are repeated example. Have a look. Have a look. Huh? Let me see. If anything I miss. Yeah, I think we are done for internal force. So I will hand over you guys to Dr. Nurul next week for static. Okay.